Welcome everyone. I'm excited to welcome you to today's presentation on HVAC systems. The title is Introduction to HVAC Systems, and we'll be exploring the fundamentals of heating, ventilation, and air conditioning. Over the course of this session, we'll cover key concepts like cooling capacity, main components, and how the air and refrigerant circulate within these systems. So, let's dive in and get started. Let's take a moment to look at some of the key design standards and codes that guide our projects. For example, in terms of comfort, we often use ASHRAE 55, which helps us ensure thermal comfort for building occupants. When it comes to energy efficiency, ASHRAE 90.1 is our go-to standard, setting the benchmarks for sustainable design. For duct design, SMACNA provides valuable guidelines to ensure proper airflow and system performance. And when we're working on projects in Saudi Arabia, we follow SBC 801, which addresses local requirements and standards. Additionally, fire safety is covered by NFPA 90A overall. These standards and codes are essential. They help us create safe, efficient, and comfortable environments that meet both international best practices and local regulations. Let's talk about how we calculate cooling loads. The basic formula is quite straightforward. Load equals area multiplied by W per square meter. For example, if we have a space that's 120 square meters and the cooling requirement is 160 watts per square meter, then the total load comes out to about 19,200 watts, which is roughly 5.5 tons of refrigeration. It's important to remember that for smaller areas, using watts per square meter makes sense because it's simple and accurate. However, for larger buildings, we often switch to BTU per ton of refrigeration to better match the scale. Also, when calculating cooling loads, we need to account for various factors like solar gains, the number of people occupying the space, and lighting loads. Each of these adds to the total cooling requirement. And don't forget, verifying the ventilation air is crucial. Proper ventilation can significantly impact the overall load, so it must be included in your calculations. Overall, understanding these principles helps us design efficient and effective cooling systems that meet the specific needs of each space. Let's take a closer look at chiller system design. First, there's a simple formula to determine the flow rate in gallons per minute, or GPM. It's calculated by multiplying 2.4 by the total refrigeration tons, or TR. For example, if you have a 100 TR chiller, the flow rate would be 240 GPM. This helps ensure your system is properly sized for efficient operation. Next, we have the primary and secondary loop configuration. This setup is crucial for maintaining proper flow and temperature control across the system. It helps optimize performance and energy efficiency. We also need to consider components like the expansion tank and air separator. The expansion tank accommodates the thermal expansion of water, preventing pressure issues, while the air separator removes dissolved air, which can cause noise and corrosion. Pipe insulation and supports are equally important. Insulation reduces heat loss and prevents condensation, which is vital for system efficiency and safety. Supports keep pipes secure, avoiding vibrations and potential damage. Finally, control sensors and valves are the brains of the system. They monitor temperature and flow, enabling precise control and automatic adjustments. This ensures the chiller operates optimally under varying conditions. All these elements work together to create a reliable, efficient, and well-designed chiller system, which is the core of effective cooling in any HVAC setup. Let's talk about package unit design. First, we have the formula for calculating air flow, which is air flow equals 400 times the TR in CFM. For example, if we have a 25 TR unit, that translates to about 10,000 CFM of airflow. This helps us size the equipment properly for the space. Next, we consider the duct layout and diffusers. Proper duct design ensures efficient air distribution, and choosing the right diffusers helps maintain comfort and air quality throughout the area. We also include a fresh air damper, which allows us to introduce fresh outside air into the system. This is crucial for maintaining indoor air quality and meeting ventilation standards. The filter and cooling coil section is vital for removing particulates and controlling temperature and humidity. Effective filtration and cooling help improve indoor air conditions and protect the equipment. Finally, we have the roof curb and drain detail. The roof curb supports the unit securely on the roof, and the drain detail ensures proper drainage to prevent water accumulation and potential damage. Altogether, these components form a comprehensive package unit design that supports efficient, reliable, and healthy indoor environments, aligning with our overall goal of creating optimal building systems. Let's take a closer look at the VRF system design. First, the formula here is straightforward. TR equals BTU per hour divided by 12,000. So, for example, if you have a cooling load of 120,000 BTU per hour, that translates to 10 tons of refrigeration. This helps us size the system accurately for the space we're working with. Moving on, one of the key features of modern VRF systems is the inverter compressor control. This technology allows the compressor to operate at variable speeds, which means better energy efficiency and more precise temperature control. Another important component is the electronic expansion valves. These valves adjust refrigerant flow dynamically, optimizing system performance and ensuring consistent comfort. We also need to consider the bus communication wiring, which connects all the system components for seamless control and monitoring. This wiring is essential for integrating the system and enabling smart system management. Lastly, the maximum pipe length is approximately 150 meters. Keeping within this limit ensures optimal system performance and efficiency, as longer pipe runs can affect refrigerant flow and overall operation. All these elements come together to create a highly efficient, flexible, and reliable VRF system that can be tailored to a variety of building needs. Let's take a look at the split unit design, starting with the basic formula. The BTU per hour is calculated by multiplying the airflow in CFM by 1.08 and then by the temperature difference, delta. For example, if we have 500 CFM and a temperature difference of 20 degrees, we multiply 500 by 1.08 and then by 20, which gives us 10,800 BTU per hour. That's roughly equivalent to 0.9 tons of cooling capacity. Next, there are some critical installation considerations. Keep piping length to 15 meters or less to ensure efficiency and ease of maintenance. It's also essential to have the proper drain slope to prevent water backup or leaks. Ensure there's adequate outdoor clearance around the unit to promote proper airflow, which is vital for optimal performance. And finally, always conduct vacuum and leak tests after installation to verify that the system is sealed correctly and operating efficiently. All of these points are interconnected. They help us achieve a reliable, efficient, and well-functioning split unit system, which ties back into our overall goal of effective HVAC design. Let's talk about the design of a window air conditioner. The key formula here is quite straightforward. Load equals the area of the space multiplied by 150 watts per square meter. For example, if you have a room that's 20 square meters, you multiply 20 by 150, which gives you 3,000 watts, or roughly 0.85 tons of refrigeration. Now, when designing the window unit, it's important to consider the wall opening. Typically, this opening should be around 1.2 meters high to ensure proper fit and airflow. Sealing the edges is crucial. Make sure to seal tightly and foam insulate around the unit to prevent air leaks, which can reduce efficiency. Additionally, a slight tilt for the unit is recommended to allow condensate to drain properly, avoiding water buildup. Finally, always perform a plug-and-run test after installation. This step helps verify that everything is working correctly and that the unit is operating efficiently. Remember, these design considerations are essential to ensure optimal cooling performance and energy efficiency for your space. Let's talk about air distribution and duct design. One key concept here is the formula for calculating duct area, which is area equals CFM divided by velocity. For example, if you have 2,000 CFM of airflow and want a velocity of 6 meters per second, then the duct area would be 0.33 square meters. Now, maintaining the right airflow speed is crucial. Typically, supply air should be distributed at speeds between 6 and 9 meters per second, while return air usually runs at 4 to 6 meters per second. This balance helps ensure efficient air movement and comfort. Another important point is the flexible connection at the fan. Using flexible ducts helps reduce noise and vibration, making the system quieter and more durable. Lastly, balancing damper adjustments are vital. They allow us to fine-tune airflow throughout the system, ensuring everything operates optimally and maintains the desired indoor environment. All these elements, correct sizing, appropriate velocities, flexible connections, and dampers, work together to create an effective and efficient air distribution system that supports the overall goal of good indoor air quality and comfort. Let's talk about testing and maintenance, which are crucial for ensuring our systems run efficiently. First, the COP, or coefficient of performance, is a key metric here. It's calculated by dividing the cooling output in kilowatts by the power input in kilowatts. For example, if we have a cooling of 10 kW and a power consumption of 2.8 kW, the COP would be 10 divided by 2.8, which equals approximately 3.6. A higher COP indicates better efficiency. Next, during testing, it's important to perform a pressure test at 300 psi using nitrogen. This helps us verify the integrity of the system and ensure there are no leaks. Also, achieving a vacuum of less than 500 microns is essential for optimal system performance, as it indicates that the system is properly evacuated and free of moisture or contaminants. We also look at the temperature difference, or delta T, between the supply and return lines, which should be around 8 degrees Celsius. This helps us confirm the system is cooling as expected. Finally, regular maintenance is key. Cleaning filters and coils routinely keeps the system running smoothly and prevents efficiency losses. Overall, these testing and maintenance steps are vital to keep our cooling systems reliable and performing at their best.